In this tutorial, we're going to be building single and multiple hidden layer neural networks using TensorFlow. Of course, before we get to the code, we're going to cover a few topics. The first one being the comparison of single and multiple hidden layer neural networks and what they can and can't learn, and that includes the linear and nonlinear relationships of data that we feed into it. After that, we'll take a quick look at the types of models that we're going to be building. So we'll have two main types of models, and we'll just take a quick look at their architectures. After that, we're going to cover problems with adding more layers. This is a problem that you encounter in deep learning. Since this particular tutorial is not about deep learning, we'll just introduce you to that aspect, and we'll cover that in more depth once we get into deep learning in future videos. Then, of course, finally, we'll move on to coding, where we're going to code a single layer neural network from scratch. And then finally, we'll code a multi-layer neural network, and we'll do that just by building upon the first one that we did. This tutorial is actually going to be split up into 2 or 3 videos, depending on the length, just so you're aware of that. Okay, let's make the comparison between single and multiple hidden layer neural networks. At any point in this video, just to be clear, if I say single layer model, something like that, I really do mean single hidden layer, so it still has the input and output with the single layer sandwich between them. Okay, so starting with the single layer models, they're really good for learning linear relationships between the attributes in your data. And when I say linear relationships, I'm generally excluding any interaction terms, which isn't always the case. Sometimes a single layer model can still be good at picking up on interactions, and we'll take a quick look at what I mean by interactions on the next slide. They also have far fewer parameters, weights, and biases, which are housed inside of each of the nodes of our layers in the model. So that means that overall it's going to be faster to train as well as faster to make predictions. So that gives us just lighter weight models overall. Also, there's no exploding or vanishing gradient problems, also known as unstable gradients. That's related to what I mentioned earlier about problems with adding multiple layers. So we'll take a look at that a little more closely just on the last portion here. For multiple layers, they're really good at learning complex relationships. So not just with interaction terms, but also with higher order relationships, so polynomial problems. With the parameters, we can end up having many millions of parameters with multiple layers, and so that can create a heavier model, something that's going to be slower to train and slower to make predictions. And that's kind of where graphics processing units came in, GPUs, just to speed that up for the greater parallelization. Also, with the multiple layers, we have to be careful of unstable gradients. Not always a problem, but sometimes it is. And slower to train. I've kind of already mentioned that with the parameters. So I just mentioned 2 different terms. I said interactions as well as polynomial. So let's take a look at what I meant by interactions first of all. If you look on the first cell, linear relationships with no interactions, you can see a really basic equation. So we have this linear equation which is b0, so think of it like an intercept, and then plus the x1, x2, etc., all the way to xn terms, where all of these b values are just coefficients of x. So that's a linear relationship with no interactions. If you look at the second cell, the with interactions, inside the red box you can see we have x1 times x2 and also x2 times x3. So those are interaction terms where we have multiplication or division of our different attributes. And then, of course, when I said polynomial, what I meant was nonlinear interactions. So if you look at that red box in the last cell, you can see that we have x2 squared. So it's basically interacting with itself. So we have the square of that, or we might have the cube and higher order terms. So that's where the multiple layers come in. They're really good at picking up on those interactions, and not just the linear interactions, but also the nonlinear with interactions. Let's take a look at how this happens, how the different number of layers are able to pick up on different terms. So we have this very familiar image at this point, if you've seen our previous videos, of this network with 2 hidden layers, as well as the input and output layers. If you look at that first hidden layer, that's where the linear terms are found, so the linear relationships with no interactions. If you were to consider that first layer as being our data, and so we have 4 attributes for this model, and each of those feed into that first layer. Because of the math that works out inside of these nodes, you basically just pick up on those linear relationships. So you would have just the different combinations of the x variables added together, multiplied of course by different weights. And while if you add a whole bunch of nodes there, you could to some degree approximate kind of higher order relationships, but it becomes really difficult and you're not going to learn quite the same as if you add more layers. So looking at that second hidden layer, that's where we get linear with interactions. So we have all of these linear terms from the first one that now are coming in, and we can get some interaction terms. This is where they can kind of start multiplying together. And then if you move on a layer further, that's where we're going to have quadratic interactions. That's where we have this x squared that we looked at on the previous slide. Now, of course, you don't want to count on an output layer as actually being able to learn or pick up on all of these higher order relationships. Generally, there really aren't going to be enough nodes for that. So while it can pick up on some, and that includes if you only had a single hidden layer for the next level of interactions, you really don't want to count on the output layer for that. Just count on it for making your predictions. That's it. Here we have a summary of the 2 different models that we're going to be building using TensorFlow. We have the single hidden layer neural network, which is going to have an input layer with 3 nodes, so that means that our data is going to have 3 attributes. We'll have a single hidden layer with 2 nodes, which should be enough to learn simple linear relationships. Our output is just going to be a single node, and that's because we're actually going to be doing a linear regression problem with this. So instead of a classifier, we're going to have a neural network acting as linear regression. And this network is going to be demonstrating learning linear relationships without interactions. We can also take a quick look, if there's time, at how it performs compared to our next model for interaction terms. So on that next model with 2 hidden layers, again, we're still going to have 3 nodes for the input because we're going to be using the same data, but we're actually going to be predicting different values because we're going to add some relationships. So those two hidden layers will have 32 nodes each. As we build up layers and we start looking for more complex relationships, we can no longer use so few nodes. We generally have to add more. Sometimes just a couple works, but generally even for simple beyond linear relationships, we need to add more nodes. And the output, again, is still going to have 1 node because we're still performing regression. And this one demonstrates learning linear relationships with interactions, but it hasn't gotten us quite to the quadratic portion yet. What we will do is add some quadratic terms just to kind of give you an example of how it can't quite pick up on that even with our output layer. And here's our look at the problems with adding more layers. So you'll see this formula in here, and you don't really need to worry about the details. All you need to know is that this is computing what's called the gradient of our cost or loss function with respect to some parameter. In this case, it's with respect to the bias, which is inside of our first layer. So part of the learning process is called backpropagation. So it computes this gradient going backwards. It goes layer by layer, and this gradient at each step is used to update the parameters inside of each of the nodes of our layers. So in this case, you can see that we have 4 layers, so we've gone 4 layers back. Now, if you imagine that if each of the terms inside of those brackets are less than 1, especially if they're significantly less than 1, and so that is going to be related to the values of our weights. So if those are significantly less than 1, then you can see that the gradient would vanish because you're multiplying a whole bunch of really small numbers together. So for example, if you had 0.1 times 0.1, etc., so you'd have 0.1 to the 4th. You're going to have a really small value, which means you're barely going to be updating whatever parameter you're computing a gradient with respect to. So if you add a whole bunch of layers, say 6 to 10 layers or even more, then you'll just get really small gradients, which means no updating. Your model, at least at earlier layers, isn't going to be learning very well. So while it learns well at the later layers, because you don't have that vanishing problem yet, as you work backwards, you will. Now, if the values are much greater than 1, then you're just going to have an exploding gradient problem. So the value goes up to really large amounts, which means it's going to be hard to reach a minimum because you're going to be updating your weights by really large values. So that is really just a summary of the problem of adding more layers. It's not always a problem, and there are ways to handle it, not to fix it or cure it entirely, but there are ways to work around it. So at this point, the video has gone to just about the right amount of time to cut here. So we'll move on to the coding in another video.